organized.
Yeah, so welcome everyone. So we are very excited to have Pinkas as our speaker today. He's going to talk about one of his recent work on PSI, specifically on Oblivious key value stores and amplification for private set intersection. Thank you so much, Bin.
Great, thank you. Thanks for the introduction. And I'll talk about private set intersection, PSI, and about this Oblivious key value store, but mostly it's about trying to find concrete parameters in which to implement cryptography. And the problem is that when you want to say implement some hashing scheme for that used in an operating system, then it's fine if like the hashing phase probability 1 in 1,000 and 1 in a million, because everything will still run well. In cryptography, you want the failure probability to be extremely small, like negligible. So you cannot run experiments. So the failure probability that you seek to find is negligibly small. So you cannot run efficient experiments to verify it. So you should either analyze it or try to do something else. And this is the problem that we encountered when doing this work. Okay. So I'll start with introduction for PSI, or private set intersection. So in general, it's the problem where you have 2 or more parties. Each one of them has a private input set, and they wish to learn the intersection of the 2 sets and nothing more. Like 2 teachers, and they both have like a student that they some suspect, and they want to check if they're thinking about the same suspect or something like that. So in general, so we have Alice and Bob. She has a list of items x1 up to xn. Bob has n items and they wish to learn the intersection while hiding everything else. And they might also wish to compute some function of the intersection rather than the intersection itself. So they want to compute the size of the intersection, or whether the size is greater than some threshold, etc. So here, I usually show several slides about applications of PSI, but I don't have time for that today. So you can think of applications like information sharing, like different companies check, compare what they see on the network to see whether they, have the same strange things happening on their networks. When you look at databases, so basically, if you do a join, it's you look at the intersection and you operate on it. When you do analytics, say for machine learning, so when you want to compute the probability of A given B, you want to count how many times both A and B happen and divide it by B. So this is like computing the intersection. And companies, okay, so Signal is using it to identify mutual contacts. When you enroll in their app, they want to see who of the current users, who of your contacts is already using Signal. So one approach is just to upload your contact list to the servers. The other one is to do PSI. They do PSI using trusted computing because it doesn't scale, but at least you get, you get at least the need. They want to find who of your contacts are using Signal because you need to communicate with them using Signal, but they don't want to learn all of your contacts. And Google are using PSI quite a bit to learn ad conversion rates. Like they have some store, and they know who came to the store and bought something after they publish it on Google, and Google know who've seen the ad, and they want to compute how much revenue was generated from people in the intersection of those who've seen the ad and bought something. Now, why is PSI interesting and why I've worked on it so much? And the issue is that unlike other problems of secure computation for which generic solutions are sufficient, in PSI, you need to compare every input of Alice to every input of Bob. So naively, you have to do n-squared comparisons, which is a lot if n is a million, etc. So trying to overcome this and try to get to something close to linear is quite challenging. And over the years, we used quite a few techniques to achieve that. So a major technique we used from the start is hashing. Now, suppose that they both know and use a random hash function, which is not secret. And this hash function hashes items into n bins. And suppose they also have like n items. So both Alice and Bob hash their items to bins using this hash function. So if Alice and Bob has this blue item, they're both going to hash it to the same bin because they're going to apply the same hash function to this item to define the bin to which it is mapped, and the same for this orange item, etc. So what they need to do, they don't need to compare each item of Alice to each item of Bob. They only need to compare the items that Alice mapped to a certain bin to the items that Bob mapped to this bin. So in general, on average, she's going to map only one item per bin. So it seems that they're only going to need like a linear number of comparisons, which would be more efficient. I haven't said how they compare, one item to one item without doing that. But at least we have less comparisons. Okay, so you have this hash function. You map the n items to n bins, and what you see here is although on average each bin is going to have one item, some bins are going to have more than one item, some are going to be empty. And you need to compare all the items that Alice mapped to this bin to all the items that Bob mapped to this bin. Now, the issue is that we would like to hide how many items each party mapped to each bin. And the reason is that just Alice telling to Bob how many items she has in each bin reveals information about her input. So suppose Seni is mapped to bin number 1, and Alice tells Bob that she didn't map any item to bin number 1. Then Bob knows that Sally is not in Alice's input. So you can do quite a lot from that. So they need to hide how many items they map to each bin. And the only way we know how to do that is to use actually to pad each bin to be as occupied as the most occupied bin. And when you map n items to n bins, the most occupied bin with very high probability is going to have log n items. Actually, you can get to log n over log n, but let's ignore that. So basically, you get that each bin has log n items. So for n bins, you have to compare log n to log n. So using the naive approach, you have to do like n log square n comparisons, which is also it's quite a lot. And we would like to reduce that. So one approach that was used to do that was cuckoo hashing. That was initially suggested by Pine and Wadler. So here it's a hashing scheme. I hope that many of you know it, where you have two hash functions, and each item can potentially be mapped to 2 locations. So you have 2 hash functions, and you have slightly more than 2 n bins. And each item can be mapped either to H0 of X or H1 of X, like 2 different bins. And this freedom actually is very useful because it's known that if you map n items to a linear number of bins, just about 2 n bins, then this hashing succeeds with very high probability. Okay. More specifically, there's a theorem saying that if we have a stash of small size, like let's say a stash of 2 additional places and 2 plus epsilon n bins, then this hashing, when you map an item either to H0 of X or H1 of X, or if both are occupied, you put it in the stash, then this succeeds with very high probability of, it fails only probability like n to the minus s plus 1, which is for s equals 2 is cubic in n, which is great. Like so n is 1,000,000, it fails probability 2 to the minus 60. So this is great as a data structure is great because to search for an item, just search for it in 2 places or in the stash. This is great, and we're actually going to use it. And this failure probability is great. For n is 1,000,000 and s is 2. This is 2 to the minus 60. That's great. However, there are 2 problems here. One is, theoretically speaking, this is only polynomial. This is a polynomial small probability in the input size. And like for the theoretically minded people, we want the failure probability to be negligible, which is smaller than any polynomial. And to be smaller than any polynomial, we need S to be super polynomial. So this destroys like the entire linearity of the scheme. So that's really bad. Now, you might say that you don't care about asymptotics. You want concrete parameters to be efficient. But what happens here is that if you look at the proof, they only prove an asymptotic bound. And if you want to instantiate it, you need to know, okay, what parameter, what constant should I put instead of this O notation? And the proof doesn't give you any hint about this constant. And you might want to run experiments, but to verify a failure probability of 2 to the minus 40 or 2 to the minus 60, you have to run more than 2 to the 40 or more than 2 to the 60 experiments, each one of them with 1 million items. That's a huge task, okay? So it's both nice, but it's also troubling both for theoreticians and for practitioners. So how do we use this cuckoo hashing? So what we do for PSI, okay, let's do it. Okay, so we have these two hash functions that map n items to slightly more than 2 n bins. So Alice is going to use simple hashing. Each of her inputs is going to put both in H0 of X and H1 of X in 2 locations. And Bob is going to use simple cuckoo hashing. So each of his inputs is going to put it either in H0 of Y or H1 of Y. This ensures that if they have the same input, say this input is mapped to bins 2 and 3, Alice is going to put this item in both bins 2 and 3, and Bob is going to put it in one of these bins. So there's going to be a match. So in one of these bins, we're going to compare and see that there is a match. Okay. The reason that they cannot both use cuckoo hashing is that Alice might decide to put the item in bin number 2, and Bob will put it in bin number 3. So then there's not going to be a match. So one of them is using cuckoo hashing, the other one is not going to use cuckoo hashing, but still we save a certain factor. And when we use this, we see that, okay, she's going to have like log n items in each bin. He's going to have like 1 item. So the total number of comparisons is going to be like n log n, something like that. Okay, so just to repeat, in each bin, Bob, who uses cuckoo hashing, has 1 item, and Alice has up to log n items in each bin. They run a protocol, which I'm not going to go into, but call it an oblivious pseudo-random function protocol, where Alice has a key to pseudo-random function. Say, you can think of it as AES, okay? So F is say AES, and Bob has an input, and he learns he has an input Y, he learns F of Y, okay? And Alice doesn't know what Y is, and Bob doesn't know the key. So you can learn an encryption of an item without telling the guy who has the key what is the item that you want to encrypt. So Bob, for each bin, he computes F of his input. This should have been F of Y1 up to Yn. These are Bob's inputs. And Alice knows the key. She can compute the encryption F of all of her inputs. So Bob gets, this for each of his items, and Alice at the end sends him F of all of her items, and he compares these 2 lists. And what happens is that Bob basically can do only n queries, so we can only compare n items. And if you believe that we have this protocol that enables to compute this function, so like AES, like encrypt the value without the key, without knowing the key, then everything is fine. Okay. So yeah. So okay. So regarding security, okay, when we do these protocols for secure multi-party computation, there are 2 types of adversaries we consider. One is adversaries which we call semi-honest, which follow the protocol. We tell them to do certain operations, they do these operations. And the other type of adversaries, which we call malicious or active adversaries, they can behave arbitrarily. So they should send, an encryption of something, can send whatever they want, okay? And obviously, malicious adversaries are more realistic because adversaries can, behave arbitrarily. But it's easier to get security only against semi-honest adversaries. But the goal is to get security against malicious adversaries. And usually, the first step is to get security against semi-honest adversaries that follow the protocol. And the next step is to get security against malicious adversaries. And this usually requires much more overhead. Okay. So when you ask why these protocols are not secure against malicious adversaries, So if the evaluation of these functions, this pseudo-random function, f or AES, is secure against malicious adversaries, then apparently there's only one issue that we're left with. Okay, so there's only one issue. Suppose that both Alice and Bob have a value z. Alice should put z in both bins to which it is mapped, both h0 and z and h1 of z. And Bob uses cuckoo hashing, so it puts z in only one of these two bins. Now, suppose Alice is malicious, so she chooses to put z only one of the two bins, not in both of them, but only one of them. So if Bob also decided to put z in h0 and z, h0 of z, then z is going to be in the intersection. If Bob decided to put z in h1 of z, then z is not going to be in the intersection. Now, Bob's decision where to put z, so he has this freedom of putting z either here or there, but this decision is constrained by the other inputs that Bob has. So we can show that there are choices of inputs of Bob that will force him to put z in this location, not in the other one, and vice versa. And this is for any two functions. You can find inputs that have this property. So basically what Alice can do if she does not follow the protocol, so this is a very subtle attack and it doesn't tell her too much. If she doesn't follow the protocol and she puts an item only in one of the two bins, then basically she computes a function which puts this item in the intersection only if Bob decided to put this item in this bin and not otherwise. So and this decision is based on other inputs of Bob. So she learns information about other inputs of Bob. And this actually, it actually happens and you cannot ignore that. So apparently this is like the only problem that was left in like 2020 to solve this. Okay, so this is what we wanted to solve. And also, what is this function f that we use, this pseudo-random function that like AES that you cannot compute without the key? So it's not going to be AES. It's a function defined by Oru, Orsini, and Scholl, uses Oblivious transfer extension, which is extremely efficient. It has the following property. It's secure against malicious behavior. It's extremely efficient. That's great. For each row of this table, the receiver Bob learns fi of x. So we have like a special key per row. And the sender can compute fi on any input. So therefore, Alice can send fi. So there's like a different key per row. And she can send f of that row applied to all the inputs that she mapped to that row. And what's important, this function has a homomorphic property. So fi of x plus fj of x of y is fi plus j of x plus y, xx or y. So if x was mapped to row I and y was mapped to row j, you have the property that if you add f of row I to x to f of row j to y, you get like f of row I plus j applied to x or y. And I plus j is larger than the number of rows, but you can define a key for that, like f with the sum of the keys to the sum of the inputs. So I don't going to describe how this works, but this is what we're using. So this is the first work that we did, PSI from Paxos. It's with Mike Wasulik, Nitriu, and Avishai and I. And this is how we use this property, how we achieved malicious security. Okay. So what we used a different flavor of cuckoo hashing that we kind of invented here. So Bob, first, he has his inputs, and he has these two functions that he and Alice agreed upon, and they're completely random. They're independent of his inputs. And he uses them to do cuckoo hashing. So each item can be mapped to two bins, okay? So suppose that he maps X to two locations, row I and row J. He will put in these two locations two values, Vi and Vj, so that the XOR of these two values is equal to X. And he's going to do it for each of his inputs. So Y, he has Y mapped, Y is mapped to here and here, and he's going to put here and here two values that the XOR is going to be equal to Y. And the problem is, of course, that the value that he puts here is relevant for both the XOR of V1 and V3 and like V2 and V3. So you have like this constraint, two constraints on the same bin. But suppose you can do that. Okay, suppose that you can Bob can do cuckoo hashing like this. So instead of retrieving X from either this bin or this bin, he retrieves both bins, XORs the results, and learns X. So this is some similar to Gabbard-Bloom filters, if you heard of this term, etc. Okay, so why is this useful? Okay, so in the PSI protocol, Bob will run with Alice this Oblivious pseudo-random function evaluation, and he's not going to learn Fi of X or Fj of X. He's going to learn Fi of Vi, whatever he put here, and Fj of Vj. Now, what we have from the homomorphic property that Fi of X plus Fj of Y is the Fi plus J of the XOR of these two values. Now, Bob put here and here two values whose XOR is X. So basically, if he takes what he learns here and here and XORs them, he's going to learn Fi plus J of X. So instead of learning F of X, Fi of X or Fj of X, he's going to learn two values, sum them, and he's going to learn F of I plus J of X. Now, why is this good? Okay, so this is good because, okay, what we said, okay, the problem we had before was that Alice would put X in just one of these two bins, or will send to Bob the F of X just for one of these two bins, and she will learn whether Bob decided to put X in the first bin or the second bin. This will reveal information to her. Here, there's no such choice to Alice. Like she has to send information for that corresponds to the two bins, and she doesn't know if Bob was asking about the first bin or the second bin, because he's going to ask something about X in this bin, also in that bin. So this, like, I didn't describe to you how to prove things about the security of PSI, but this was like the only remaining issue that Alice can like do this selective failure for Bob. Like he will learn something, something will be in the output if Bob puts X in here, but it's not going to be in the output if Bob put X here. And in the new protocol, since you combine the two values, then either thing is, X is in the output or not, but Alice cannot learn in which bin Bob decided to put X, because Bob essentially put two halves of X in the two bins. Okay. Now, the issue remaining is whether this is possible, because each of these bins might have many values mapped to it. So we have to kind of set values so that this is possible. So to see if this is possible, let's look at cuckoo hashing. So for cuckoo hashing, what people did, they use something which is called the cuckoo graph. Okay, so this is the table. And you have the hash functions, two hash functions. So X is mapped, say, to these two places, okay? So each item in the table is going to correspond to a node, okay? And if X is mapped to node number 0 and node number 3, we're going to have an edge between nodes 0 and 3. So each location in the table corresponds to a node. And an item which is mapped to two nodes is essentially an edge between these two nodes. So X is mapped to 0 and 3, so we have this edge between 0 and 3. And A is mapped to nodes or entries in the table 1 and 3, so we have this edge between 1 and 3, etc. So basically, you take a table, you take the hashing functions, you have a set of inputs. Each input defines an edge between two entries in the table. So each entry in the table is a node, and each input defines an edge between two nodes. So you get this graph. And people working on cuckoo hashing, what they proved that cuckoo hashing is successful if in each connected component in the graph has at most a single cycle. So for instance, here, cuckoo hashing will be successful because we only have a single cycle here. If we had like another edge between here and here, then like an item was mapped to nodes 0 and 7, then cuckoo hashing wouldn't have been successful. So this was done in the cuckoo hashing literature, and all the analysis of when cuckoo hashing succeeds or not is based on analyzing random graphs and looking for these properties. Now, what we need to do, we need to assign values to the nodes so that, okay, under the following constraints, x, which is mapped here and here, okay, actually implies the constraint that the value here plus the value here, the XOR of the two values is going to be x. And the value we put in node 3 and the value we put in node 1, the XOR of these two values should be equal to a, and so on. So basically, we put a set of constraints on the values we should put in the table, and we should somehow solve this. So apparently, there's an easy way of solving it, which is called peeling, and it's not something that we invented, or maybe we reinvented it. It goes like this. Suppose this is the table, we cut it to like two subtables, and these are the edges. So like X is mapped to this entry and that entry, so we have an edge between them. And maybe A is mapped to these two entries, etc. And we have to set values to the nodes, so value here, etc. So that's we have this constraint. So the value here and the value here, the XOR is going to be equal to whatever this edge is equal to, etc. So what we see is that, like in this graph, a leaf, like this is a leaf because this node has only one edge going into it. Okay, so there's only one constraint. So we can fix values to all other nodes in the graph. Okay, after we fix values to all other nodes in the graph, the only constraint remaining is this constraint that the XOR of this and this should be equal to something. So for this node, we didn't have any constraint for it, so it's still free. After we set all the rest of the graph, so we already have a value here. So we need to set this value so that this value, so with this value will satisfy this constraint. So that's easy because we have like one constraint in one node. So basically, all leaves, like we can we know we can handle them at the end of the process. So just take them out and look at the graph without these leaves. This is like the peeling process. So we take out all edges that touch leaves, and we get a simpler graph. And in this graph, like this edge before it was, it didn't touch a leaf, but after we took out these edges, this edge touches a leaf. So we know that after we handle all the rest of the things in this graph, and we set this value to something, we can set this value so that this constraint, this red constraint will finish. And the same here, etc. So by doing this peeling process, we can basically it's a recursive process when we remove nodes and edges from the graph until we get to a very small graph. And hopefully we can finish the entire graph here, and the overhead of fitting everything is going to be linear. Okay. Now, what happens if we are left with a cycle? Like there's no node of degree 1. So we need here to put values that satisfy these 4 constraints. And apparently this is impossible because the equations we have here are not linearly dependent. And this is because we need to do it like XORs, so we only have 0, 1 coefficient. So I looked at it, for a long time. There's no way, there's no way to solve these things. Okay, so we stuck. Okay. The nice thing, okay, what we stuck with is essentially we stuck with what's called the 2 core of a graph, which is the maximum subgraph where each node has a degree of at least 2. So basically the subgraph of all cycles and all paths connecting cycles. So all the edges which are not in the 2 core, we can handle using peeling, which is very efficient. We just stuck with the 2 core. Now there's a theorem that in a random graph or random Kuka graph of size order of n, with high probability, the 2 core of size only log n, order of log n. So that's great because, when we handle everything except for something of size order of log n, okay? And handling something of size order of log n, it should be efficient. Even if you have like quadratic overhead, whatever, it's going to be efficient, okay? And we have like efficient solution for that. So based on this theorem from, random graph theory, we end up with very small core, and we can handle it. So what did we essentially do? Okay. Basically, we had the random assignments of n constraints to slightly more than 2n variables, so that each constraint involves only the sum of 2 randomly chosen variables. And all constraints must be satisfied, but we know that very high probability they can be satisfied. And this peeling satisfies all constraints with probability, which is with an overhead which is linear. That's great. And we had this theorem, which is also great, but actually it's not that great. So look at these red things. So the graph is of linear size, but we don't know how large it should be. The 2-core is of logarithmic size, but we don't know what the coefficient here is. And this happens with high probability, but the guys, the lazy guys who prove theorems about cuckoo hashing didn't bother to prove anything about the constants and the exact probability. And it's not that they're lazy. We don't know how to do it. At least I don't know how to do it. Okay, so for someone who is interested in theory, this is only relevant if this probability is smaller than any polynomial. And we don't know how to say that. And for someone who wants to implement this, then these guys wants to know, order of n, but like 2 times n, 3 times n, and log n, like 2 times log n, whatever. And what should this probability be, right? Or what should I put in these constants to make this probability smaller than 2 to the minus 40? So we're stuck here both theoretically and practically. Okay, so we try to generalize and improve this. I just should say that when we were stuck at this point, at some point we did a huge analysis because our colleagues at TU Darmstadt had a cluster of computers which was free. So we spent more than 2 million core hours to actually find the concrete probability for certain set of parameters. But obviously you cannot do it all the time. But so because if you want to verify that the failure probability is smaller than 2 to the minus 40, you have to do more than 2 to the 40 experiments on huge graphs. It takes a lot of time. Okay, and what I'm going to show here is like an approach to amplify this failure probability or this. So what we're going to do is we cannot prove. So it's anytime you're going to use some probabilistic property in building some cryptographic scheme, you want to know what's the failure probability. So in some cases, you can compute the exact failure probability. Like for, I don't know, birthday problem, you can compute the exact probability. Okay. In some cases, you only have like an asymptotic probability, or you don't even have an asymptotic analysis. In these cases, you have to basically somehow instantiate your parameters, but you want to make sure that your concrete probability is smaller than some constant that you care about. And unfortunately, this probability is usually very small, like 2 to the minus 40, 2 to the minus 80, etc. So running experiments is extremely costly. Unlike people working in systems where they're happy with failure probability of 1 in 1,000, we need to run much larger experiments. So what I'm going to show in the rest of my work is an approach to somehow amplify this, build like, at least for this problem, smaller instances of this problem for which there's going to be a high failure probability, but it's easy to verify high failure probability. Like if I want to verify a failure probability of 1 in a million, I can run 1 million experiments, or more than 1 million experiments to verify this. And this I can do on my laptop. And then I'm going to combine several of them and prove that the failure probability of the combined construction is as small as I need, like 2 to the minus 40, 2 to the minus 80, etc. So this is the approach that we took. So this is this new work from Crypto 21 with Garimella, Michael Sulek, Nitu, and Avishai and I. Okay. So this OKVS, Oblivious Key Value Store, it's happening a lot in PSI. So we need to store pairs of keys and values while hiding the keys. So like send you some data structure. If you query it for a specific key, you're going to get a value, and I'm going to hide the keys and random values that corresponding to them. And you should learn whether you ask about the key or not about the key. So let me show you examples. So basically, I have a set of keys and values, n of them. I encode them in some data structure. And then the decoding feature should be that if you ask about the key, you get the corresponding value. If you're asking about a key that I didn't encode in here, you get a don't care. I don't care what you get. If these are random, then the property I want it to be is that if I give you this data structure, you don't know which values are encoded in it. So I encoded n values in this data structure. If you ask about them, you're going to learn the outputs that I encoded. Okay. If you ask about other things, you're going to get, I don't care what you get. And you should learn which items I encoded here. And the thing is, if these outputs are random, then based on the outputs, you shouldn't be able to, they're not going to tell you which items I encoded there. And the data structure itself should tell you what I encoded there. So one example for such a data structure is a polynomial. Like suppose what I can do, I can interpolate a polynomial that goes through these keys and say P of key 1 is going to be value 1, P of key 2 is going to be value 2, etc. Then I'm going to interpolate and send you this polynomial, just the coefficients. Now, if I send you a polynomial, you don't know what were the points over which I interpolated to get this polynomial. Now, if you evaluate the polynomial in key 1, you're going to get value 1. If you're going to evaluate something which I didn't use for the interpolation, then you're going to get something. I don't care. But you're not going to learn which values are used for the interpolation. And if these outputs, these values of the polynomial on these keys are random, then you don't know what I use for the interpolation. So polynomial is one option, but we want to do it more efficiently. So this OKVS, we have this input-output pairs, and we're going to somehow encode them using M values. And we're interested in linear OKVSs that for an input for key K, you're going to take a linear combination of the inputs. You can think that this is this data store. And for each input, you get a set of coefficients that you multiply with this data store and you get an output. And actually, we're going to use here like a binary OKVS, where basically this linear combination is just going to get a subset of them and XOR them, sum them together. Now, what you want this data store to be as small as possible. So if I want to encode n items, I want the size of the data store to be as close as possible to n. So with the polynomial, that's great. For encoding n items, I only need n coefficients. What I also want is that the encoding time is going to be efficient. And then for polynomial, that's not so great because you have to do interpolation, and this takes you time even if you use FFT. And we've been there, we've done this with polynomials before. And for encoding, decoding also should be efficient. Okay. And for these PSI constructions, we must use a binary OKVS where we just take choose a subset of items and XOR them. Okay. So one example was polynomials. Another example is a random matrix. So what we're going to do is we're going to take a random matrix, and this is the data store. And the probability is going to be that for key 1, we're going to have a random set of coefficients. And if we multiply them, this could be 0, 1 coefficients, multiply them by the data store, we're going to get V1. And the same for key 2, etc. What we're going to get is that the encoding time, we have to solve linear equations. So it's going to be n to the power 3. It's going to be cubic. Decoding time, n squared. And basically, if we take a random matrix and so to encode n items, we use slightly more than n rows here, or slightly more than n, then the failure probability is very small. So if it's like a binary OKVS with 0, 1 values, this matrix can be solved. So if we add like 40 rows, it's 39 rows, it can be solved with probability, and the probability that cannot be solved is 2 to the minus 40. So this, in terms of size, it's great. In terms of encoding time, it's very bad. And polynomials are also great in size, but also bad in terms of encoding time. Now, what about this Paxos or this cuckoo hashing thing? So each key is mapped to 2 locations, okay? And the decode just to take the 2 locations, XOR them. And we can encode using peeling in linear time. So that's great. So the encoding time here is great. The size of a cuckoo hashing, you need the table size to be 2 times n. So it's more than n, it's 2 times n, not n plus something, but that's also not bad. Okay. And we have this theorem that if the probability, if the 2 core is not, okay, if the probability of the 2 core being more than 2 log n is smaller than epsilon, which means that it's very small. So if the 2 core is very small, we're going to have a very small set of cycles at the end. And if the size of, then we can get we can work well with the linear storage. And then we can decode successfully, encode successfully with only with negligible error. Okay. Now we want to translate this to concrete parameters because this is great. And again, this thing about the 2 core, we don't have like a concrete analysis is this, oh, we don't have a concrete analysis, so we don't know what to do. So in this previous work, we used heuristics with these huge experiments. And we found out that if we get table size of size 2.4n, then the probability of the encoding failing is like 2 to the minus 40. And this is for n, which like in a million or so. Okay. So actually, there are more efficient cuckoo hashing constructions. For instance, this is like a very nice construction from 2021, saying that if we use like cuckoo hashing with 3 hash functions, it was known before to be more efficient than with 2 hash functions, but this is an analysis saying that we can, so with 3 hash functions, each item is mapped to 3 locations in the table, not only 2. And this reduces the size of the table from like almost by a factor of 2. But this was like an empirical analysis, and there are no concrete parameters to use. So, but we would like to use it because, like, it's much better. So what we would like to do is something like, okay, that except with very small probability, we would want to use this 3-way cuckoo hashing, and then we can map like 1 million keys to say 1.3 million beans with less than 10 keys in the 2 core in the final cycle. And so we want to do experiments and claim this with confidence of 0.99999. So this is something we would like to claim, because if we have claim like this, we can use this in our constructions. But the guy who proved this didn't prove the parameters, and running these experiments would also require us to get like 2 million core hours, which is, we cannot get, they don't come easy. So so here we actually had a problem. And actually many previous papers, they just use heuristics here, all previous papers. Okay, so verifying this claim is very resource intensive. Okay, and if we want to the failure probability to be 2 to the minus 80, then it's also extremely, extremely, we cannot verify this. So what we can verify is a claim about smaller tables. Okay, so what we can run experiment is to say map 1,000 keys to 1,300 beans, and show that the probability of 1,000 keys, when we do this mapping, the probability of having more than 2 keys in the last 2 core in the last cycle is smaller to 2 to the minus 15. So this is, we can very easily verify, because this just means running like 2 to the 15 or maybe 2 to the 20 experiments. Okay, and the experiments are with 1,000 keys, so I can run them with Python on my laptop. That's very easy. Okay, so this is thing we can verify, and somehow we want to amplify to this claim about large tables. Okay, so we want to compose empirically verified smaller OKVS into larger OKVS. So here's one example, then we can do it more efficiently. So suppose we use 2 tables. Okay, so these are completely independent tables. Okay, this cuckoo cuckoo tables, completely independent hash functions. And the way we're going to map items, so to retrieve an item, I try to retrieve it from this table. I get a value. I try to retrieve it from this table. I also get a value, and I XOR the two results. So usually with three-way cuckoo hashing, I take three values from here, the locations to which this item was mapped, XOR them, and this is my answer. Now I'm going to take the answer from this table, the answer from this table, and I'm going to XOR the two results. Okay. So I decode from this table, I decode from this table, and I XOR. Now, suppose if both of them succeed, there's no problem. Suppose I fail, my hash functions are such that the end keys I want to map to this table do not map well. I end up with a very large cycle in the end. I cannot, things do not work well. So here I have a failure. I don't know what to do. But so then I'm going to put in this table completely random values because I don't know how to put my inputs there. Okay. But suppose in this table, I succeed. The hash functions are such that my hashing works well. Okay. So what I'm going to do, I'm going to put in this table random values. And then the requirement is what I retrieve from here and what I retrieve from here. The XOR of the two is what I need to find at the end. So what I put here, I'm going to say, okay, I have this final output I need at the end to learn at the end, this value that should be associated with key A. Here I put random values. I only put the random. I know what I'm going to get from the first table. And in the second table, I encode whatever value I want. So for A, I'm going to encode a value so that this value, so that its XOR with the values I put in the first table for A is going to give me the required output. So in the first table, it's going to give me for A R2, XOR R3, XOR R5, because A was mapped to these three locations here. What I want to retrieve for A is this value of A. So in the second table, the hash functions work well for me. So I'm going to put there that it's going to retrieve for A this thing. And since the final thing I'm going to do, the way this hashing works is that you retrieve a value from the first table and from the second table, and you XOR the two. Sorry. Then from here, I'm going to get this junk for A. From the second table, I'm going to get what I put here, which is the value I should get from A XORed with the junk I'm going to get from the first table. And when I XOR the two, I get the right value for A. So the thing that happens is that if I fail in one table and I succeed in the other, I can change the values I put in the second table to compensate for the random values I'm going to get from the first table. And what enables me to do that is that at first I can check whether the hash function work well or not for A in each of these tables. So here, the probability of me failing on, so if hashing fails for one of these two tables, okay, then that's okay because I can set the second table to compensate for it. So so failing for the entire structure, okay, will only happen if hashing fails for the first table and for the second table. So if failing for one table happens probability P, failing for both of them will happen probability P squared. So I get this amplification. So if P is 2 to the minus 15, failing for both of them is something like 2 to the minus 30, which is better. And I just need to check that I failed for one table, probably 2 to the minus 15, which I can easily check. Now, this is not that great because by doing this, I basically use twice as much space. So basically, I get a table of size which is double. So like this is one table, second table, I use twice as much space. That's not good. I want to use not much more space than for one table and still be able to reduce the failure probability. So here is what we do to achieve that. So we have n key value pairs, and we use the hash function, say h1, which map the n keys to 3 sets, 3 bins. So each one of them is going to have like n over 3 items, because this is a random hash function that we define in advance. Okay, so these n items are going to be mapped to 3 bins, each one of them of size n over 3. So each one of them, we're going to define this OKVS, this key value store, that you put a key and you get a value. Now, for an item which was mapped to this bin, the way we're going to retrieve the final value is we're going to retrieve a value from this key value store and from this top key value store, which I haven't said what I'm going to put there, but I'm going to retrieve a value from here, a value from here. I'm going to XOR the two, and this is going to be my final output. For an item I put here, I'm going to retrieve a value from here and a value from the top, and I'm going to get this final output. And the same, if a value was mapped here, I'm going to retrieve a value, something for it from here, something for it from here, and XOR the two. So this is like a star. This is like the center, and like many things coming out of the center. So to decode a value for a certain key, if A was mapped to the first table, then to decode it, we decode something from this N1, we decode something from N0, and we XOR the two. If A was mapped to the third table, then we decode something from here, we decode something for here, and we XOR the two. Now, how do I set values to these tables? Okay, so one thing to note is that the total size I have here, it's only 5 times n over 3. This was like 1/3 each one. So I had n items, each of these tables is n over 3. So I didn't increase the size by much. And if I was using like 100 tables here, then I would have increased the total size of the table by only 1%, because I would have had 101 tables, each of them of size n over 100. So if we can encode, if in both of the, if all 3 tables in the bottom, each of them had keys that can be successfully encoded into it, then what I'm going to do, I'm going to put here completely random values, and I'm going to put here things that together with what I have here will work well. So I put here completely random values, and suppose I had a key A that was mapped here. So what I should retrieve for A from this OKVS should be a value that if I XOR it with what I retrieve for A from this OKVS will give me the right answer. But basically here I can encode whatever value I have. So initially I put here completely random values, and here I put whatever values I need to put so that the XOR with this will give me the right answers. And the same here. I had here random values, and for each item which was mapped here and here, I can encode here whatever I need to compensate to the random values here. Now, the interesting thing is what happens if one leaf fails, say this leaf fails. Then the thing I'm going to do is first I'm going to put completely random values here, because I cannot, the items that were mapped here, I cannot properly map them to this table. I cannot, so I just put random values here. Now, for this N0, if somehow I didn't fail here, okay, but failure is something that happens with small probability, say to 2 to the minus 15. So I don't expect it to happen too often. So here for N0, I'm going to put values that are going to compensate for the failure in N1. So for each value that was mapped to N1, I'm going to put here values so that the XOR of what I get from N0 and from N1, the XOR of the 2 is going to get what I need to get for this value. And afterwards, I'm going to put values in N2 and N3 that compensate for the items that we map here to what I put in N0, and the same for this. So basically, if I have a failure in just one of these 4 tables, I can compensate for it. If I have failures in 2 or more of these tables, then I cannot compensate for it. And the guy who's doing the decoding doesn't know where the failure occurred. This guy only takes, an item was mapped here, so it retrieves something from here, it retrieves something from here, and XORs the 2. And the same for each, for each item. So the failure probability is basically like p to the power of 2, okay, times the number of pairs of, 4 choose 2 pairs of tables times p to the power of 2. So it's like p squared, and then p to the power 3, but that's even smaller, etc. So you get a failure probability which is p squared. Okay, and you only increase the size by 1/3. Okay, so then we actually instantiated it for 1 million key value pairs. And what we did, we used like 160 bins at the bottom instead of 3. Okay, and then we could run experiments. Okay, so we run experiments, and okay, this is something we can easily like theoretically verify. Like we map 1 million items to 130 bins, 60 bins, you can verify that you're not going to get in a bin more than 6,600 keys with this probability. This is something you can actually calculate. And then for each bin, we only have at most 6,600 keys, and we only need to okay. And the bad event is that the bin is going to have more than log n items in it. So, sorry. Okay. We want the total probability to be 2 to the minus. Okay. Got it. Okay. For each bin, we run experiments that verify that the failure probability is 2 to the minus 30. And this is because the number of items in the bin is relatively small. And this failure probability is 1 in a billion, is also relatively small. We can verify it. Okay. Combining this with all bins gives that the failure probability for the entire table is 2 to the minus 45, because the entire construction fails if we had 2 failures. Now, each of these, we have like 160 bins. Each of them fails probability 2 to the minus 30. We want that failure is going to happen at most one of them, and you do the math, and you get the probability is 2 to the minus 45. The failure will happen for more than one bin. And this is like already my last slide. So this is like a statement we can verify concretely, and we're sure about it. So basically, we can encode 1 million key value pairs. It takes like 3 seconds, and we are sure that this fails with very small probability. So all previous works were heuristic. This is the first time we have like concrete guarantees. So this thing can be used, like almost all works on PSI use polynomials to basically do these key value stores. So whenever we use polynomials, we can replace them with this OKVS, okay, which are much more efficient to compute. Instead of doing like polynomial interpolation, we just do these linear operations. And with this privacy simplification, we can verify that the failure probability is indeed very small. And okay, and when running this on 1 million items, okay, this was faster by a factor of say 1.6 compared to what we had in the previous year. Okay, and actually, what's also very interesting here is that here we got secure. We did in this work 2 things. One is we had security against malicious adversaries, and also we had this amplification and this 3-way cuckoo hashing. Okay, so basically what we got is we got security against malicious adversaries almost for free, because once we use 3-way cuckoo hashing and okay, actually let me restate this because I wasn't accurate. Okay, we improved it over previous constructions because we used 3-way cuckoo hashing. Okay, and so this is extremely fast. Also, compared to previous constructions, we use this peeling approach, okay, which is much more efficient than polynomials. And using this amplification, we are sure that the failure probability is very small. Also, the only difference between the semi-honest and the malicious versions is that for the semi-honest, you can put an item in one of 2 locations. Here we have to put it in the 2 locations and take the XOR. So the difference is very small. So what we get for PSI, that we get security against malicious adversaries, which doesn't impact performance at all. Okay. What I should say is that it does impact how simple it is to understand the protocol, and so how simple it is to implement the protocol. So what I tell people who want to use PSI is usually, if you want just to get like good performance, you can use very simple protocols. If you want like to push to the best performance, you have to use these tricks and similar techniques, which are more complicated to understand and to implement. But at least, you know, we only have to do it once. And the nice thing is that we can get full security against malicious adversaries without affecting performance. And I think that this is the last slide.
Yeah. Thank you so much, Mini, for the talk.
Thank you.
Yeah, so maybe we can use some time if the audience has, if any of you has a question. Actually, I will start because I was really interested in the peeling algorithm, and it's kind of like you have written it on the side of a slide where it's kind of like solving a system of linear equations. And this is exactly true. And because I know that the community, at least like in random matrices, they use so many tricks from the algorithmic theory and exactly random graphs in order to solve, because they use Gaussian to solve the linear equation, and this is n cube. And in some times, like when the matrix has some structure, which is exactly the case in peeling, because you have like two kind of like constraints, in some cases more, so you can solve it in a more efficient way. So I was interested to see if there are more results, like in some sense, like that kind of like the math community like used to improve their you know, rank calculation, how the complexity is used, how much complexity it is like to solve this linear equation, because there is almost like a mapping between the two in some sense.
So yeah, so this peeling is you know, has linear overhead for solving this system of linear equations that have this structure. It's as far as so the paper I cited from 2021, it's extremely nice. It was a paper in SODA 2021. I forgot the name of the author, but it's extremely nice techniques. And what you get is that, if I recall correctly, you had like about if each item is mapped to 3 places in the hash table, then the hash table should be of size 1.3n for peeling to work. Now, they know that for this mapping to succeed, you can actually work with slightly smaller tables, slightly smaller than, so they're like 2 bounds, one for the mapping to succeed and a slightly larger bound for peeling to succeed. Okay, but the difference is very small. I think that with this construction, you get almost the same same bounds. Okay, I have to say something about, okay, just to say something about this construction from 2021. They achieved this 1.2.3, I think, n bound by choosing the 3 locations to which an item is mapped, not uniformly at random, but using some a different probability. Okay, very simple one, but different probability, and then they prove it. And then when I saw it, I got extremely excited, and then I did something which I very, very rarely did. I just sat and implemented it like that the evening I saw it, and I started running experiments, and it didn't work. So it performed worse than the simple peeling with uniform probability, uniform hash functions, and then only when I set n to be large, like in the millions, did it start performing better. Actually, I remember this because I initially implemented the version which was of peeling, which was not very efficient. So the runtime was not linear, and so it's not working. So you have to, I want to check it for larger input. So then I had to re-implement it because it didn't run fast enough for millions, especially not in Python. So this is an example of for result where the asymptotics are very good, but they don't work for small values of n. So this is something you have to take care of. Also, something that you have to take care of that is that the failure probability many times is like n to the power of minus s, where s is the size of the stash or something like this, which is very small if f is in the millions, but it's not that small if f is like 10,000. So then you should be careful, because for smaller inputs, this hashing is gonna fail. I mean, you might say that you don't care about smaller inputs because for them you can use less efficient solutions, but you shouldn't just blindly use this hashing for smaller inputs because it's gonna fail. So in general, what I'm saying, I mean, you should take these results that they have and try to examine them, see where they use asymptotics, and try to get a feel for what you need.
That makes sense. Yeah.
Yeah, I had a question. So the paradigm that you kind of introduced with this amplification of the failure probability, I mean, you motivated it, from the point of view of cryptography, but isn't it interesting just in general, even for like algorithms as well? I mean, it seems like maybe we should be just thinking about this in general, like when we're designing data structures, right? Just as a even when it's not security related, no? Or
I think so, but I think that we are a unique place because we care about small failure probabilities. Like you look at, I mean, it was kind of, you look at these papers and have these great results, but it's only about asymptotics. Like they are like, first you have like initial results and it's like all of this and all of that. And then you look at systems papers that do an analysis, like they do actually measurements, but they only measure for things that failure probabilities that for us are quite high, but for systems are good, like 1 in 1,000. If your cache fails in 1 of 1,000 tries, then this doesn't matter so much, I guess. If you have a cache miss, for each 1,000 cache, and times you go to the cache, that doesn't matter too much. For us, if your data leaks, if your data leaks for 0.1% of your customers, that's not that good.
Mm-hmm.
So it might be that we are a unique place here.
Mm-hmm. And isn't there, do these issues come up in the ORAM schemes that use Google hashing as well? Because there's also something with the failure probability not being negligible, right? Or the some of the bounds not being negligible. Is that?
I think so. So one area where like one issue that happens then is that the ender, the size of the size of the number of items you map is usually it might be small for ORAM. You have to make, depending how you use this cuckoo hashing, but if you kind of start to use smaller and smaller sets, it might be small. But otherwise it might be, they might have the same problem. Yeah. So even this n to the minus s plus 1 failure probability, if you use a stash of size s, is you don't know what is the constant coefficient in the O notation, and it's polynomial, which is extremely annoying. Yeah, because even if you want a theoretical results, that's annoying.
So just a follow-up on what Seni was saying. Does it mean like in these cases, so because like the way how I understand cuckoo hashing is that like you write your s in general as function of n, which makes things even worse, because sometimes like in ORAM, like your stage as log n, where now like n is the number of items, but now it appears in your asymptotics, and you want to make everything small. And as you were saying, like n usually it's not sometimes it's big, but usually it shouldn't be assumed always to be big. So does it mean that, for example, for all of these types of ORAM, for example, the hierarchical ORAMs and all of these constructions, type of hierarchy, like where they use some cuckoo hashing in there, does it mean that to avoid, in general, like dealing with heuristic, does it mean, for example, that you just need to assume your stash size to be something big just to avoid this case? Just to make sure that your failure probability is always...
So I haven't so I haven't looked into ORAM for a while, but you have to do, so you have to take n into account. And you also need, so this n to the minus s plus 1, you need to, it's order of, so you need to find what is the asymptotic. So I guess if you run, a million experiments and nothing fails, and then you say, okay, I'll increase it a little bit more, then probably the fail probability is good enough. But if you really want to verify it, it's, I don't know how to do that. Yeah.
That's interesting.
Yeah, thank you. So no, this
I had many papers where I just used these asymptotics without taking, thinking about, what are the actual numbers we should put there. But it is a problem.
Yeah, I think that we are already like a little bit over time. Thank you so much, Benny, for making the time and giving the talk. Thanks again.
Yeah. Thanks for hosting me.
Yeah, of course. It's a pleasure. Bye.
Bye-bye.